What Ibn al-Haytham did was take the principles of geometry with its rules governing straight lines and apply them to the real world. He then designed experiments which would test whether the real world measured up to his mathematics. In about 1020, Ibn al-Haytham published his groundbreaking geometric explanation of light in his Kitab al-Manadhir, or Book of Optics. And what really marks this book out as science is that Ibn al-Haytham carefully justifies his theories with detailed experiments that others can repeat and verify. He starts from first principles to find out how light travels. For his first experiment, Ibn al-Haytham wanted to test the idea that light travels in straight lines. Now, to do this, he took a straight tube on which he'd drawn a straight line down the side and a ruler, again with a straight line down the length of it. And by matching the two together, he was convinced then that the tube was straight. Now, if he uses it to look at an object, in this case a candle, he can see the candle through the tube, which is good evidence that the light is travelling up in a straight line. But just to be sure, he then blocked the end of the tube. And then, by looking at the candle again, of course, he can't see it, because what this does is confirm that the light doesn't travel to his eye via any other route in a curved path outside the tube. Proof that light only travels in a straight line. Now, this might sound quite trivial and obvious to us, but Ibn al-Haytham was starting from first principles. Then, through experiment, he extends his light travels in straight lines idea to many other phenomena. He explains how mirrors work by arguing that the angle the ray comes in at is the same as the angle it bounces off at. He explains what we now call refraction, why objects look kinked in a glass of water, arguing that light rays bend when they move from one medium to another. And then he tackles the nature of vision. Ibn al-Haytham wanted to understand how an object makes an image on the retina of the eye. So he built what he believed was a stripped-down version of the eye, which is basically a black box with a tiny hole in it. This is what we call today the camera obscura. He next took his subject, in this case Anna, who's very brightly lit, and we now go inside the box to see what the image looks like. Now that I'm inside the camera obscura and I've allowed my eyes to get used to the dark, we can open the hole. And there we clearly see the image of Anna waving on the screen. But the image is inverted because light travels in straight lines, and so the light from her head has to move diagonally downwards to hit the bottom of the screen, and light from her feet travels diagonally upwards to hit the top. But more importantly, what this proved to Ibn al-Haytham is that there's a one-to-one correspondence between every point on the object, on Anna, and every point on her image on the screen. Just like a modern scientific paper, the attention to detail in the Kitab al-Manadhir is incredible. His book isn't just a dry scientific treatise, it's a manual for future generations. In his work, he constantly justifies his theories about light with experimental observation. And he describes his experiments in great detail so that other people can repeat them and confirm his ideas. His message is, don't take my word for it, see for yourself. I believe that Ibn al-Haytham was one of the very first people to ever work like this. This, for me, is the moment that science itself is summoned into existence and becomes a discipline in its own right. What I find so impressive about Ibn al-Haytham is how once he arrives at his mathematical theories, he then uses them to extend our knowledge of the real world. So, for instance, he used his new ideas about light to deduce that the Earth's atmosphere is of a finite thickness, and he even estimated what that thickness is. He did it basically by measuring how long twilight lasts. He rightly assumed that the reason it continues to be light after the sun has dropped below the horizon must be because its rays bend as they enter the Earth's atmosphere. The length of twilight and an educated guess for what we today call the air's refractive index gave Ibn al-Haytham a way of estimating the thickness of the Earth's atmosphere. He came up with a figure of around 40 kilometers, about half of the modern value. That's pretty impressive. It really shows how mathematics extends the power of science to explain. On my journey so far, I've been overwhelmed by the sheer intellectual ambition of medieval Islamic scientists. When their leaders asked them to find out the size of the world, scholars like al-Biruni used mathematics in startling new ways to reach out and describe the universe. And as trade and commerce boomed, scientists like al-Razi responded by developing a new kind of experimental science, chemistry. But if there's one Islamic scientist we should remember above all others, it is, in my view, Ibn al-Haytham, for doing so much to create what we now call the scientific method. The scientific method is, I believe, the single most important idea the human race has ever come up with. There is no other strategy that tells us how to find out how the universe works and what our place in it is. Of course, it's also delivered technologies that have transformed our lives. So the next time you jet off on holiday, or use a mobile phone, or get vaccinated against a deadly disease, remember Ibn al-Haytham, Ibn Sina, al-Biruni, and countless other Islamic scholars 1,000 years ago who struggled to make sense of the universe using crude mirrors and astrolabes. They didn't get all the right answers, but they did teach us how to ask the right questions. In the next episode, I travel to Syria and northern Iran to find out about the great Islamic scientists who revolutionized astronomy, making it a truly modern science. And I'll also discover how the man many consider to be the father of the European scientific renaissance, Copernicus, borrowed from Islamic astronomical theories. And I'll unravel the mystery of how the golden age of Islamic science came to an end.
And that final episode of Science and Islam is here at the same time next week. Jerry Robinson is here with another Moneymaker next tonight on BBC4. And on Radio 3 now, Donald MacLeod explores the work of Handel, this week's Composer of the Week.